Hi, I'm Sam Roberts from Roberts Geospatial Engineering. Today we're going to take a look at sonar bathymetry data that was collected during the search for Malaysia Airlines MH370, which went down mysteriously, it is believed, off the west coast of Australia. The data that I'm going to look at, I downloaded some years ago. It was probably 2019. I don't know how you acquire the data today or whether it's still available, but at the time it was publicly available. So we're going to look at that data in ProRaster Scientific, because today you can do virtual gridding in ProRaster Scientific, and 5 years ago I thought, with this particular data set, it's so hard to grid it. Wouldn't it be good if you could just grid it using a virtual technique? Today, we can do that with ProRaster Scientific. So let's just look at the original rasters that were supplied. So I'm going to create a new raster source, working in ProRaster Scientific. I'm going to add a raster source. I'll call this MH370 original DEM, or original bathymetry. Hit the tick and that validates that you got the right name. I'm going to select all of the TIFF files. Can anybody see TIFF? There it is. Select all of the TIFF files from a folder where I have these. So here they all are. Now these files are between 40 and 80 meter cell size, so quite low resolution. Bear in mind that that's about the size of the plane, so the plane would fit into one grid cell in these files. Now they're also all in different coordinate systems, so when I hit OK, it will display them, and it's going to display them incorrectly, because in a raster source you can't mix data that has different coordinate systems. So that's incorrectly displayed. I should, I suppose, provide a warning. But what we can do to fix that problem is to go into raster processing and do a join. I'm going to select that raster source that I just created. I'm going to make an output file called original TIFF bathy. Hit OK, and now we have the data correctly located. So let me add in, let's say, some just OpenStreetMaps. Let's move this up. So here you can see the scale of this survey. This is the search zone out here. These are the tracks as they went to and from Perth, which was the home port for the vessels. And here's Australia. So you can see that the search zone is comparable to the size of Australia, which is enormous. And perhaps, on that basis, we shouldn't be unsurprised that they have not yet located the plane. So creating grids. Let me turn off the imagery. So creating grids is really quite problematic for this data set because it's huge. And there are more than 4 billion data points collected. And so the data supplied by the original contractor is in multiple grid files for different UTM zones, and at fairly low resolution and not particularly good quality. You can see there's a lot of texture in the grid, most of which would be noise. And your chances of, if you're using this to look for the plane, which of course was not the purpose of collecting this data, the actual search for the plane was conducted by people, actually looking at the raw sonar sweeps as they came in and searching for those, signals that are indicative, or reflections that are indicative, or bright reflections indicative of a aircraft debris field. So that's how they actually look for the thing. But this was created as kind of a byproduct of that survey procedure. So that's that's the original rasters. Let's go and take a look at the point data. So let me just grab one here. They are in text files. So here it is in Notepad. So they're just latitude, longitude, and this is a depth. So this is a positive depth below sea level. And I have 9,211 of these files. And so we're going to import those into an MRP file so that we can work with them in ProRaster and then grid them on the fly. So I'll just show you quickly how to do that. So I go import multi-banded points. We're just going to do a very small example. We're going to pick up all the text files in a directory. So I'm going to go to that examples directory. Here's those text files. I think there's probably 20 or 30 or so. My output file name, so we'll call this example points. Come into here, we've got one header row, so we'll skip it. Autofill the columns. The first one is latitude. The second one is longitude. The third one is depth. And we need to specify that these are the Y columns, the X columns, and the Z columns. Now I'm going to use a data conditioning filter. I'll show you it in a minute. Because these are depths positive below sea level, I prefer them to be in RL coordinates, so they would be negative below sea level. So I'm going to use a transform in a data conditioning filter to just multiply the input data by -1. So I'm going to use this depth to bathymetry transform that I've defined. The coordinates are in lat long. We need to set a cell size. This is in lat long, so I'm going to use a 1 arcsecond cell size, which is 1 on 3600. And lat long coordinate system. Won't bother with anything else just for this example. So it imports that data, creates your MRP file, and then displays it. So let's look at depth. We'll do, say, a equal area transform. Let me just come in and change the point size to something a bit bigger so we can see them on your screen. So as we zoom in, we see more and more points until we get into the actual returns. So let's see that here with the tooltip. So you can see this one, -4,764. So you can see these side scan sonar sweeps. And it continues down to close to -6,000 meters deep. Elsewhere -3,000 meters. So there's a lot of bathymetry, a lot of terrain in that data set. So that's just an example of how to do it. Let me just show you quickly the data conditioning filter. So here it is, depth to bathymetry, and all I did was enable a transform with a scaling factor of -1 and a translation factor of 0. So we just multiplied our depth coordinates by -1 to get something that's compatible with bathymetry. So that's an example. Now, what I then did was run that with on all 9,211 files. Gives me an MRP file. It's a 28 gigabyte file, and we go now to RL or something like that. So there's our point files and MRP file. And as we zoom in, we see more and more points. and right down until we see the individual sweeps of the sonar. Coming into statistics, let's have a look at statistics. So we have here the number of valid points, 4.638 billion valid points in this data set. So it's a very large data set and it's hard to grid. But today we can do virtual gridding. So, so let's do that. I'm going to close this down now. Just a note on hardware before I go on. You can't run this on a Commodore 64 and expect everything to just work. You need some reasonably decent hardware to work with large data sets of this size. And just as an example, I can tell you what I'm working on. I have a mini PC. It's a NUC. It cost me $660 US. It has 64 gigabytes of RAM and SSD, and it has a Ryzen 7 8-core CPU. So it's not an expensive machine, but it is a relatively powerful machine, and it's capable of doing this kind of work. Anything less than that, you're going to struggle a little bit more. So you do need reasonable hardware to do this kind of work. So I'm going to go into the virtual gridding and might just start from scratch. So I need to bring in my MRP file. There's my output MVR file. I'm just going to do triangulation. We're going to grid the RL channel. I'm going to use a small tile size. My cell size, I'm going to keep at the cell size that I used for the MRP, which is 1 arc second, about 30 meters for the time being, just for this first run. So there's our grid. So it's done this in real time. It's just gridded that data at that scale. And as you zoom in, let's have a look at it full screen. And I must remember that my face is in the bottom right hand corner. As you zoom in, it will regrid and access data at higher and higher resolution. So as we zoom in, you can see more points are brought in. And then we can look at the data gridded at the full resolution of the data set. So let's come back out. I'll just zoom right back out again, come back in and go to that grid that I just created, and we'll edit it again. So we probably need some clipping. Something like that, perhaps. Maybe smaller. Let's go 0.2 to 0.2. So we're clipping by distance, and then we can bring down our cell size to look at even higher resolution gridding. So hit OK. It's updated. So let's come in, perhaps focus on this little feature. And as we zoom in progressively, we see more and more information. And now we're right down, and you can see the triangles that are being created as a part of the Delaunay triangulation gridding process. And we could go to, with Delaunay triangulation, we can choose any cell size that we want. We can go down to infinite resolution, and all we'll see from this point onwards is better and better definition of the triangles, which is not really useful. But that's using triangulation as a gridding technique. Let's now move to minimum curvature. So doing minimum curvature on a raster data, on a point data set of this size is not easy. Very, very difficult. But with virtual gridding, you can do it. So we need to, with minimum curvature, we need to choose a reasonable cell size for interpolation between data. So I'm going to go back to my normal cell size of 30 meters. We'll start with that and hit OK. So here we are, minimum curvature gridding. Now let's zoom in on that same feature that we were looking at before. And I should just turn that tooltip off because that actually will degrade performance. And now you can see that we've got a smoother, although still, quite noisy result as we're gridding. So let's do a comparison between this is our virtual grid, and let me add a layer for the original TIFFs, and then we'll zoom in on that same feature and we'll do a comparison. So let me go into swapping. I'm going to flip. So there's the virtual grid using minimum curvature, and there's the grid that was supplied by the contractor. Quite different. There's a lot of noise in this grid that's been supplied. I think that the virtual gridding is actually doing a better job. But the real advantage of the virtual gridding is that I can now explore this data set at any scale that I want to in real time, and I know that I'm working from the very highest resolution data. I'm going down to the original points, and I'm getting everything that I can out of this data set. It doesn't mean that you're going to find the plane. I think that's an impossible task with this data, but it certainly means that you'll be able to explore the geology and explore the bathymetry features of this huge and extraordinary data set. So it's taken a long time, but 5 or 6 years ago I thought, it would be great if you could grid this data in real time using a virtual gridding style process. And finally, that capability is now available. It's in ProRaster Scientific, and you can purchase it today from the Microsoft Store and do this kind of thing yourself on data sets of your own. So thanks for watching.